Embedded security is often seen as incredibly complex, with engineers asking themselves the constant question of how secure is secure enough? Answering that question starts with truly understanding the topic of security. How can we simplify growing that understanding and implementing it in our systems? We've spent a lot of time on the current talking about security and the importance that it's really having in the embedded design area over the last couple of years, and how much more important I see that getting. And with that, anytime I get a chance to talk to another security expert in the industry, I like to jump at it. And today I have the privilege of speaking with Patrick Carrier, who's the application marketing for IoT security at Infineon, and is someone who's spent a lot of time in this area, learning a lot about security and training engineers on how they can include security in their embedded systems. So Patrick, thanks so much for joining me on The Current today.
Yeah, thanks, Todd, for having me. It's great to be here and to talk with you and talk with your community here. So.
Yeah, and I think, like I said, this is such an important topic. It's something I'm trying to still wrap my head around in a lot of ways and grow my knowledge. I feel like I've come a long way from where I started when I kind of started this journey in 2016, 2017. But I wouldn't say I've arrived by any stretch of the imagination, which is why I love to have these conversations. So today I kind of wanted to focus a little bit more on the basics of security and really get down to the nuts and bolts of it. And I know you've got some interesting concepts on how to look at embedded security and simplify it a little bit for us as engineers. I think you've kind of called it the Ohm's law of security is kind of the way you're looking at things, which I think was really, really fascinating, a really cool way of thinking about it. Can you kind of talk to me a little bit about that and maybe kind of spell it out a bit for me?
Yeah, so I mean, a lot of people, it helps if you go break it down into the basics, into the fundamentals, and pretty much all engineers out there, that's where they start. They start with Ohm's law, right? The voltage, current, resistance, power, and they learn those fundamental concepts, and you build everything out from there. When it comes to security, it's no different. We actually have just a couple of key pillars, right? That everything is really built upon. We have the concept around symmetric cryptography. You have asymmetric cryptography. You have hashing algorithms. Those are the core concepts, if you will, that really help. Everything else when it comes to security is built up on top of. So you start talking about wanting to do things that are more advanced, like secure communication. Well, that's using those fundamental concepts. That's just at a higher level. And then, in between all of that, there's the small but mighty random number, right? So, and having a really good random number as a seed is really important in all of these things. So those are really the core fundamental concepts and the Ohm's law of cryptography, if you will.
Right.
And then
right.
what we do with those things, that's what determines how we implement things from a use case perspective into an embedded system.
Right, right. And so in that you're looking, I think you and I have talked in the past and how random is random, right? And without
Right.
being a number generator, within your system, is it really good enough? How do engineers take those kinds of things into account?
So I've actually seen a comic a little while ago, and it said, it was a little line of code, and it said, output random number, output 4 chosen by fair dice roll, right?
Right, right.
And it's like, well, is that really random? A dice roll, you've got 1 to 6, right? Is
right.
Just choosing number 4, is that random? And it can be, but you could guess the number 4, right? On a scale of 1 to 6. When you talk about having secure systems, having that good seed number, making sure that it's an appropriate bit length, for the application, making sure it's using the right type of algorithm for what you want to accomplish is important. And there's trade-offs and benefits especially if you break down symmetric and asymmetric. So symmetric cryptography relies on a shared secret. That means you have to have the same sort of secret on both ends of a communication path, right? But it's very, very fast, right? So there are going to be trade-offs and benefits. With asymmetric cryptography, you have 2 different keys that work together, and that means that you don't have to have the same key on both ends, right? So There is different things used for different purposes when you talk about these fundamental Ohm's laws, right? So just like you might, you might have voltage you need in one part when you're doing calculations for designing a system, voltage may be the important thing.
Right.
But somewhere else, resistance might be important, especially you start talking about matching networks, right?
Right.
Now resistance and other factors are more important, right? So the same thing can happen when you talk about cryptography, right? So in some cases, symmetric is more important. In some
Right.
cases, asymmetric is more important. In some cases, hashing. And then eventually, these all kind of culminate together, and this is how you start to design a system. In this
Right.
case, you're talking about having a secure system with secure architecture.
Right. And you touched on it a little bit just a moment ago, but maybe you can just take a second and go into when would an engineer want to be focused on doing asymmetric versus doing symmetric security?
So I'll start off by diving a little bit more into symmetric. So symmetric, I mentioned you have to have a shared secret. That means you have to have something that's common between two systems that want to communicate with each other.
Usually a key, right?
Right. Now, the problem is since you have to have the same piece of information on both ends, you have what's known as the key exchange problem, right? So how do
Right.
you arrive at that shared secret? And there's different methods and ways of doing that, but it does create a fundamental problem. It's that adage of, the best kept secret is one that's only known by one person, right? So
Right.
as you
Right.
start to proliferate that secret, then the chance of exposure increases, right? Asymmetric keys, on the other hand, they're very good about this key exchange problem because you have a public key and you have a private key, right?
Right.
And generically speaking, public keys generally are used for two things. They're used for encrypting data and verifying signatures. Now, I'm not getting into the specifics of algorithms or anything like that, but just generically speaking, when you talk about public keys, that's more or less how they're used. Private keys do the opposite. They're the ones that decrypt, and they are the ones that sign things. So that's the more security critical operation. Well, guess what? You can use asymmetric keys to help solve that key exchange problem for symmetric keys, for example.
Right.
Because you
Right.
can share a public key and it's public. It can be used to verify signatures, making sure things came from an authentic source. And it can be used for encryption, right? Since you can do the opposite with private keys, then what that means is that you can then encrypt a symmetric key, for example, transfer it, sign it, and basically it creates this whole the solution to this key exchange problem that you have, right? So
Right.
because you can use these you can use these things together, basically,
Right.
right? So
Right. Right.
so it's
So it sounds so basically the way I would envision it if I were doing a system is if I've got, if I know I need fast data transfer at some point, I want to eventually get to symmetric
yep,
communication because it's much faster communication going on there. But I don't, maybe I don't have symmetric, I don't want to share the keys everywhere easily. Maybe, my two users have never talked to each other before. So to get symmetric, they've got to somehow share a key. And so then you pass the key using asymmetric security. Once the key is passed, you switch to symmetric. That would be
yeah,
kind of
and
a way of doing that.
yeah, and that's one implementation of it. I mean,
Right.
there's this whole classic example of Bob and Alice, right? So,
Yes.
not
Yeah.
to dive into who is Bob and who is Alice, but I
Right.
mean, for your viewers that want to learn more, there's a whole there's probably 100 videos out there
Oh,
that
there's great
explain.
videos on that. Yeah. No question. Yeah.
Um, but also there's hashing, which is important. So a lot of people, most people understand the concept of like a checksum. Well, all a hash value is a cryptographic checksum. It's important for knowing when things are in transit to make sure things haven't changed, right? So basically, if you have a blob of data, so all a hash algorithm is it distills that blob into a check value, basically. You
Right.
change one bit in that blob of data, the algorithm spits out a completely different number. So it's deterministic based on the algorithm, but it's not where you can make minor changes and get a deterministic result, right? So
Right.
it's
Right.
really good for that checksum sort of value.
Right.
And then you combine that with a private key, basically, and that's how digital signatures work, right? So
Right. Right. Okay. Makes sense. And so, and I think that kind of goes hand in hand with my next question, which is, you know, when we're looking at securing a system, it's important to take consideration what it is we're securing.
Yep.
So if I am securing two laptops that are sending, communications between, two locations, maybe something secure, maybe something you don't want out there, maybe some intellectual property that you're sending from place to place, you want pretty hefty security versus a light bulb where maybe it's less of an issue. So how should an engineer kind of look at those kinds of things and make considerations on the security based on the application type?
Well, a light bulb is one that I really like because a lot of people they think, oh, a light bulb. What happens if someone hacks that? It's
Right.
going to be some hobbyist or somebody who wants to play a prank. They're going to turn the lights on and off, and they're going to have their fun with it. And, what could that hurt? And it's like,
Right.
well, yes and maybe not, right?
Great. Great.
Because at the end of the day, a light bulb, what is it connected to? It's part of a larger system, right? So, and a lot of people think, well, your laptop, of course, you need to have security in your
Yeah.
laptop. Your laptop has all these features and functionality built into it, but it's also connected to other systems, right? So it's not
Right.
necessarily just the compromise of the device itself that you're talking about, but also how does that interconnect with other parts of the system, with other things in that same network?
Right.
So there's been some very famous high-profile hacks where
Yeah.
people have gotten into say the HVAC system,
Hmm.
and that allowed them to access other parts of network traffic because now they're actually able to compromise the network itself.
Right.
The other thing to think about too with a light bulb is it's not just a light bulb in your smart home, for example, and it's not just the attack surface of somebody turning your lights on and off, right? What is that light? Where does that light bulb sit? Is that light bulb in your smart home, or is that light bulb in a government building, right?
Right.
So, what is the actual setting and the use case and the application of the light bulb itself? A light bulb, a lot of times, your security system is connected to your lighting system. And the
Hmm.
reason they do that is because, let's say, a security sensor trips, right? Well, the first thing that happens usually is the lights turn on. So when the police show up, the area is lit up, and they can proceed and they can investigate, right?
Right.
If the police are called. Well, guess what? If somebody compromised your lighting system, you still tripped a security alarm because somebody broke in somewhere. Well, if it's dark out and the lights aren't on, the police may hesitate. They may say, "Wait, we're going to wait for backup." Well, now
Right.
the bad guys are getting away, right?
Yeah. Right. Exactly. Yeah.
So there's a couple of different ways to think about this. When you think about it from a holistic systems point of view, it's not just a matter of a light bulb versus a laptop. It's how are these things applied? What are they connected to? You really have to start to think about the whole ecosystem.
Right, right. And I think a big part of that, you're obviously very involved with IoT, things like light bulbs, which have changed so much over the course of the last 15 years. But, when you're talking about incorporating a wireless device like a light bulb or whatever other object in your house, maybe it's a ceiling fan or a refrigerator or a toaster or whatever it might be, there is an element and an aspect of that IoT process where you've got to provision that device. And that can be certainly, I think, an area of weakness in the security is that that provisioning portion of the design. What are some of the risks that you see associated with provisioning, and what should engineers be considering in the provisioning of their IoT systems?
Yeah, so that's actually a really good topic. So when you think about a IoT connected device, so a lot of times when you're talking about IoT connected devices, most of the time it's wireless. It can be wired,
Sure.
but generically speaking, when you think about IoT, you have some sort of connection, and it's usually some device that can actuate or sense something, right? Those are the let's say the generic, most classical example of what an IoT device is. Now, if you
Sure.
think in those terms, the other thing that you have to start to think about is with your question of, well, since I have devices that can sense or actuate and they're connected, these devices need to have their own identity so that I know in the case of a light bulb, I'm talking to light bulb 1, 2, 3, A, B, C, whatever it may be, right?
Right.
You need to
Right.
know that each individual light is its own unique entity. So what that means is each light bulb or each IoT device needs to have its own unique identity itself.
Right.
The way that's typically done today, and especially if you're talking about devices that ultimately connect to the cloud, is with certificates. right?
Right.
So certificates that are embedded into a device. Now comes the provisioning problem that you're alluding to here of, well, how do I create these certificates? It's more than just a serial number. We are starting to talk about cryptographic things with certificates, because a certificate more or less acts as a container for a public key, and it's
Right.
usually got a signature on it. And now security is starting to get real, and it's starting to get something tangible that engineers can use and ultimately have to deal with if they've not before, right? Um, some of the things we're doing at Infineon is we're trying to make it easy, right? So
Yeah.
we operate our own certificate authority. Now, we also will work with customers that have their own certificate authority if they already know what they're doing. We can work with that as well, but we'll actually do pre-injection of certificates and keys and those sorts of
Right.
things into devices. We've even gone so far as to have standard off-the-shelf products that still have their own unique identity, but they're provided in a form that is claimable by the end user. And by
Right.
the end user, in this case, I'm talking about designers, right? So, or whoever's doing the manufacturing. Now, that could potentially be extended if you wanted to. In some cases, some end products want to offer services to you as a consumer. So you go to Home Depot, you buy this fancy light bulb, and it's got some services tied to it, right?
Right.
So that's a different use case altogether, but that exists out there as well. So, but the point is here that we have, one of the products that we have is like our Optica Trust M Express, and it's
Right.
designed with the intention that this is 90% of the time going to be used in a system connecting to AWS or Azure.
Okay.
So
Okay.
out of the box, you buy this chip, you put it in your system. It actually comes with a QR code that allows you to scan it and claim that certificate. What this helps prevent the situation of, since we're shipping a device that has its own unique certificate anyway, well, normally you'd have to read that certificate out, you'd have to build a manifest file, you'd have to pipe that into AWS, and logistically it creates multiple points of failure, right?
Okay.
By giving us this ability where you can claim these devices, we already know what certificates are on the devices, so we give you the ability to download that manifest file. And through our platform, where you claim those devices, you can actually set up automated provisioning where it's not where you have to download that file and then you have to go and load it yourself. We can actually enable you to automatically pipe that into your cloud system. So after some initial setup, all you have to do is you have to just log in, scan a QR code, and you're done.
Right. Okay.
Right. So,
Very
and then
nice.
those credentials, you log into your AWS account and you look, you just claimed 4,000 devices. Those 4,000 IDs now are in your AWS account and they're ready to go. So,
Right. Right.
um, the other cool thing about this is it helps with the lost chips scenario. So if you ordered something that was pre-provisioned, customized for your exact use case, now these are Todd's chips, right?
Right.
Well, what happens if those get lost in transit? Well, now Todd's got 4,000 rogue chips out there somewhere. Well,
Right.
in the case of where you claim it at the time of consumption, you don't have to worry about that, right? So that's the advantage of this kind of late binding or claiming at time of manufacturing as well. So
Right.
there's
Right.
some other unique security problems that are solved with this sort of approach as well. So
Right. Okay. And I mean, it's huge for just, intellectual property theft and deterring that as well. So, just it sounds like definitely a great way to go and making that easy. Because I know that's one of the biggest problems as we talk to engineers is even those, the engineers that have figured out, okay, I know how to do security. I know how to secure my system, but actually moving that into the production process can become a bit of a nightmare.
oh yeah.
Because how do you actually do that in the production side?
Yeah. So, and some of the things that we're doing even, starts to, take us into more specific applications. So you'll see some other products from us that are ideal for wireless charging, Qi 1.3 certification. You start
Sure.
talking about a lot of these standards are coming out with requirements that are really pointing you in the direction of having your own public key infrastructure set up. And there's a cost associated with that. It's expensive for you to do it
Yeah.
yourself, right?
Yeah.
So, and that's something that we've got the knowledge, the know-how. This is not new business for Infineon. We ship tons of devices a year that are used in applications like payment, like ID. A lot of these IoT applications, they use the same concept. So Qi wireless charging's one. We've got emerging Matter standards for smart home,
Mhm.
and more that are just really starting to drive some, requirements in the direction of you need to have a PKI, right?
Right.
So
Right. Oh, very cool, very cool. And I think, it's interesting, all those standards, and now we've got a lot of government agencies getting involved, and different governments around the world coming in and saying, we're going to start putting these different certification standards on embedded systems. That's, I think, going to evolve and continue to drive a lot of this as well. I think you said it very well when we spoke the other day. The application doesn't require security to work properly, so it's not something that your end user sees as a feature. It's just getting to a point where it's going to have to be accepted and a little bit mandated, or the end user's not going to want to pay for it, and the companies building the products aren't necessarily going to want to do it. So it is something that we've got to look at mandating a little bit, I think, amongst ourselves as electrical engineers, to ensure that we've got good security in our systems, and that we don't have bad actors that are able to abuse the great things that we create.
yeah, yeah,
Important.
and I would say that on the topic of, let's say, government regulation and all of that, the good news is some of the, let's say, organizational bodies for some of these applications. I mentioned Qi, I mentioned Matter. Those help start getting us in that right direction. But in some cases, you do have to get governments to actually start to mandate things. Now, usually from a government perspective, what we've seen so far is they're a little bit looser on the requirements. So in the U.S. here, they point to NIST a lot of times and NIST standards.
Right.
And those do leave some degrees of flexibility in there, but they also start to get very specific. So when I say flexibility, a few years ago, it started off, well, you shouldn't have the password be password, right?
Right. Right. Yeah.
Uh, you should have a semi-randomized password, so
Right.
things start off generally fairly loose, and then they start to get more and more specific over time. That's the trend that we've seen, right?
Right.
Now, that being said, if you want to future-proof yourself, then instead of just going for the bare minimum requirements, we always recommend designers, well, look at what some of the optional requirements are, and bake those in ahead of time, right? So
Yeah.
that way you don't have to change your design a year from now, right?
Exactly.
Because if
Yeah.
it's in there as a hard requirement today and then an optional requirement today, it doesn't take long before those optional requirements start to make the list of required, right?
Exactly.
So
Get ahead of it.
uh,
Yeah.
so, and some of the ways you can think about that too, if you want to have longevity in your product life cycle and your product design, is to, and with security, this is of the utmost importance. It's not about protecting your system from the attacker of today. It's the attacker for tomorrow, right?
Right.
So,
Right.
so you want to future-proof yourself anyway, when you think in terms of what security is right for your application.
Right. Absolutely. Absolutely.
So,
No, and that's what we've all got to be thinking about. And again, I think it all comes down to, are you planning to secure your system? If we're not
yep.
thinking about it, we're going to end up in a bad place. I think we've all got to really put, as we're starting a design, any design, we've got to sit down and think about, what am I doing to secure this? What am I going to do from day one? An ounce of planning is going to go a very, very long way, in helping you. It's not going to happen by accident. So I hope we
Yeah.
as engineers continue to get better at it.
Yeah, so I would say the happening by accident is kind of like, initially when I started with this a few years ago, a lot of people would tell me, it's like, well, I'll just have my security be something obscure, that way people can't reverse engineer. And it's like, well,
Right.
we've actually learned over time that security through obscurity doesn't work, because there's
Right.
always the potential for somebody, if somebody can go to the local store and buy your product, that means that they can, even though it costs them money and you say, hey, I got a sale out of it, they can always deconstruct it, figure out how it works, and eventually they're going to figure out your obscure means how that
Exactly.
thing works, right?
Yep.
So using known, good, proven techniques is important. Using some of these fundamentals that we've been talking about, asymmetric, symmetric, and hashing, good random
Yep.
numbers. Basically, when we talk about good random numbers, source of entropy is the term that you want to look for. Is do you
Right.
have a good source of entropy?
Yep.
And that's how you can start to really make sure, at least at the fundamental level, what you're building is good, right? So
Yep. Yep. No, it makes perfect sense. Patrick, thank you so much for your time. I really appreciate you sharing some of your expertise. I think we could talk about this for hours. And certainly I think we have. We've done a lot of episodes on security, and I think we'll probably do a lot more because it is something that I think is so important. Thanks so much to our listeners today. Really appreciate you joining us for on the current. If you are looking at implementing security into your embedded system, or if you have a new design and you just have questions on it, we at Future Electronics would absolutely love to help you with that. Introduce you to our own engineering experts and also experts like Patrick, and help you figure out exactly what you should be doing to add security into your system and anything else that you might be doing in your embedded design as our discipline continues to advance and evolve. So thanks so much for joining us on the current today. If you have any questions for us, please reach out to us at shaping the future, one word, shaping the future, at futureelectronics.com, and we'd be happy to connect with you. So thanks again, Patrick. Appreciate your time, sir, and we'll talk to you on the next episode of The Current.